Hello friends, today's topic is Principal Component Analysis PCA. PCA is a Principal Component Analysis. Basically, PCA is a dimensionality reduction method that is often used to reduce the dimensionality of large data sets by transforming a large set of variables into a smaller one that still contain most of the information in the large set. So, reduce the number of variables of a data naturally comes at the expenses of accuracy. But the trick in dimensionality reduction is to trade a little accuracy for simplicity because smaller data sets are easier to explore and visualize and make analyzing data much easier and faster for machine learning algorithms and without extraneous variable to process. So to sum up, the idea of PCA is simple: reduce the number of variables of a data set while preserving as much information as possible. Okay. So the main advantage of PCA is that once you found these patterns in the data and you compress the data, that is by reducing the number of dimensions without much loss of information. Okay, and PCA is a way of identifying patterns in data and expressing the data in such a way as to highlight their similarities and differences. So these are the steps by step explanation of PCA. First step is standardization. The aim of this step is to standardize the range of the continuous initial variable so that each one of them contributes equally to the analysis. More especially, the reason why it is critical to perform standardization prior to PCA is that the latter is quite sensitive regarding the variance of the initial variable. That is, if there are large difference between the range of initial variable, those variables with large range will dominate over those with a small range. For example, a variable that ranges between 0 and 100 will dominate over a variable at range between 0 and 1, to which will lead to biased result. So, transforming the data to comparable scale can prevent this problem. We can reduce overfitting with the help of PCA. So mathematically, this can be done by subtracting the mean and dividing by the standard deviation for each value of each variable. We will discuss this through an example so that you can clear your doubts easily. So this is a formula: value minus mean upon standard deviation. Once the standardization is done, all the variables will be transformed to the same scale. Step 2. This is the covariance matrix computation. The aim of this step is to understand how the variable of the input data set are varying from the mean with respect to each other, or in other words, to see if there is any relationship between them. Because sometimes variables are highly correlated in such a way that they contain redundant information. So, in order to identify these correlations, we compute the covariance matrix. So, the covariance matrix is a P into P symmetric matrix, where P is the number of dimensions. If you have dimension 2 dimension, then you have to create a matrix 2 by 2, and if you have three dimensions, then you have to create 3 into 3 matrix, covariance matrix. That is 3 into 3 matrix of the form. The covariance x-axis, covariance xy, covariance xz, covariance yx, yy, yz, zx, zy, zz. Since the covariance of the variable with itself is its variance, covariance A equals to variance A in the main diagonal, the top left to the bottom right. Okay. So we actually have the variance of each initial variable, and since the covariance is commutative, the entries of the covariance matrix are symmetric with respect to the main diagonal, which means that the upper and the lower triangular portion are equal. What do the covariance that we have as entries of matrix tell us about the correlation between the variables? It is usually the sign of covariance that matters. If positive, then two variables increase or decrease together correlated. If negative sign, then one increase when the other decrease, inversely correlated. Okay. Now that we know that the covariance matrix is not more than a table that summarizes the correlation between all the possible pairs of variables. Let's move the next step. So compute the eigenvectors and eigenvalues of the covariance matrix to identify the principal components. So eigenvectors and eigenvalues are the linear algebra concepts that we need to compute from the covariance matrix in order to determine the principal component of the data. Before getting to the explanation of these concepts, let us first understand what do we mean by principal components. So principal components are new variables that are constructed as linear combination or mixtures of the initial variable, and these combinations are done in such a way that the new variable, that is principal component, are uncorrelated, and most of the information within the initial variable is squeezed or compressed into the first component. Okay. So the idea is 10-dimensional data gives you 10 principal components, but PCA try to put maximum possible information in the first component, the maximum remaining information in the second, and so on, until having something like shown in the screen plot below. So first principal component get more priority as compared to last PC1 principal component. So first principal component has most higher priority, then second, then third, then fourth, and so on. And the last is just less priority. So how PCA constructs the principal component? As there are as many principal components as there are variables in the data, so principal components are constructed in such a manner that the first principal component accounts for the largest possible variance in the data sets. For example, let us assume that the scatter plot of our data set is shown. Can we guess the first principal component? Yes, it is approximately the line that matches the purple marks because it goes through the origin, and it is the line in which the projection of the points, red dots, is most spread out. Or mathematically speaking, it is a line that maximizes the variance, the average of the square distance from the projected points, red dot to origin. The second principal component is calculated in the same way with the condition that it is uncorrelated with perpendicular to the first principal component, and that is accounts for the next highest variance. These are, we will discuss in a numerical part also. Okay, so these are the way to calculate the variance, eigenvectors and eigenvalues. So next step, feature vector. As we saw in the previous step, computing the eigenvector and ordering them by their eigenvalues in descending order allow us to find the principal component in order of significance in this significant. In this step, what we do is to choose whether to keep all these components or discard those of lesser significance of low eigenvalues and form with the remaining one a matrix of vectors that we call feature vector. So the feature vector is simply a matrix that has columns, the eigenvectors of the component that we decide to keep. This makes it the first step toward the dimensionality reduction, because if we choose to keep only p eigenvectors out of n, the final data set will have only p dimension. Okay. Thank you.